Let's start where we left off in the previous video with this lead and cadmium redox reaction. We already went over which species is being reduced, which is oxidized, and what the total potential is for this reaction. Remember again what the total potential, or E naught total, actually means physically. It's an amount of energy per unit of charge. Like as these negatively charged electrons are moving, some amount of energy needs to be added, which is why delta or E naught total for this reaction is negative. And also recall Gibbs' free energy change and spontaneity. Delta G and E are related through this equation here. Delta G naught equals negative NFE. N is the molar coefficient of electrons being transferred in the reaction, and F is Faraday's constant, 96.5 kilojoules per volt mole. A reaction will proceed spontaneously without the need for energetic input if delta G is negative. If delta G is positive, the reverse reaction occurs spontaneously. So for this example here, the forward reaction isn't spontaneous, but the reverse reaction is. For this next part, I'm going to want to focus on the spontaneous reaction only. So imagine I have two beakers, one filled with 1 molar lead sulfate solution and the other filled with 0.5 molar cadmium sulfate. On their own, these are just boring salt solutions. But then, say I dip a piece of solid lead in the lead sulfate beaker and a piece of solid cadmium in the cadmium sulfate beaker. Now they're just boring salt solutions with some metal chunks in it as well. But then I connect the two solids with a wire and the solution with a salt bridge, which I'll talk about briefly in a bit. And ta-da, I have an electrochemical cell. So what happens here is that the solid cadmium produces some cadmium ions and some electrons. Those electrons move through the wire to the lead side and react with lead ions to form more solid lead. Because aqueous ions are being reacted or produced, we need a salt bridge to provide counter ions to balance the charge in solution. In theory, given enough time, you'd run out of solid cadmium or aqueous lead ions, and the reaction is over. But while the reaction occurs, those electrons are moving from the cadmium to the lead, actively producing an electrical current. Because this is a spontaneous reaction, we call this a voltaic or galvanic cell. Both of the solid metals in an electrochemical cell are called electrodes. Specifically, there is the anode, where oxidation occurs, in this case cadmium, and the cathode, where reduction occurs, i.e. lead. My mnemonic for this one is anode starts with oxidation, oxidation start with vowels, and cathode and reduction start with consonants. The electrons will always move from the anode to the cathode. From the anode, because that's a result of oxidation, and to the cathode, so that it's used in the reduction. So we can take that earlier E total equation as E total equals E of reduction minus E of oxidation, and now we'll call it E cell, which is E cat minus E an for cathode and anode. Remember, in a voltaic cell, E cell must be positive in order for delta G to be negative, spontaneous. And therefore, E cat should be larger than E an. Voltaic cells are neat because they can convert chemical energy into electrical energy. But what about the opposite case? Can we apply electrical energy to a chemical reaction to make the reaction occur? We absolutely can, and that's actually how we store chemical energy in batteries to be used later. In this case, we will have a non-spontaneous reaction, so delta G will have to be positive. E cell then is negative, and therefore E cat will be smaller than E an. The way that this will work is by connecting each electrode to a power source and grounding reservoir, like a wall socket. That power source will apply voltage, sending electrons to the cathode, pushing reduction forward. In turn, at the anode, metal ions in solution will be oxidized to form more solid, and the extra electrons get sent back to the wall socket. Then we remove the power source and keep the circuit closed or open until we want to use that stored potential energy. When we complete the circuit, reconnecting the anode and the cathode, that energy can be released and electrons will flow once again. This is called an electrolytic cell, requiring energy to be put in. While these pictures are nice to visualize an electrochemical cell, they're not exactly a quick way to show what we're talking about. So for that reason, we have cell notation, which is just a shorthand way to describe an electrochemical cell. The form goes as such: the solid anode, phase change, aqueous ions that go with the anode, salt bridge, aqueous ions that go with the cathode, phase change, and solid cathode. So back to our lead and cadmium cell, the cell notation for that looks like this: solid cadmium, phase change, 0.5 molar CD2 plus in the aqueous solution, and the salt bridge, 1 molar lead 2 plus aqueous and phase change then to solid lead.